Hi guys, if you are viewing my channel first time, please subscribe to my channel for more updates on embedded systems. And today we are mainly discussing about on jump, loop and call instructions. Okay, these are the branching instructions. If you want to move our microcontroller control from one place to another place, mainly these branching instructions can be used. Today we are going to discuss about these instructions one by one today. Okay, first one is the looping. Repeating a sequence of instructions a certain number of times is called a loop. For example, this looping concept is not available. This sequence of instructions we need to write multiple times. Due to this, our code memory may exceed. Why? Because we have within 4 kilobytes of memory in our 8051 microcontroller. It may exceed if this looping concept is not available. Okay, that's why we should understand about this looping concept. We can reduce the code memory as much as possible. Okay, looping action is performed by this instruction djnz register comma label. Okay, here decrement jump if not 0. First we are decrementing the content of the register by 1. After the decremented we are just checking if it is 0 or not. If not 0 we are just moving to this label referred by the address. Okay, first one is we need to decrement the register value. If not 0, jumps to the target address mentioned by this label. Okay, prior to start of the loop, the register loaded with the counter for the number of repetitions. Okay, before starting any loop, we need to mention the one of the counter that should be loaded with some value. And counter can be R0 to R7, can be used for the counting applications. This program adds the value 3 to the accumulator 10 times. For example, this is my statement 10 times. For example, if this looping concept is not available, I need to write this instruction 10 times. Add a comma 03. Okay, instead of writing this 10 times, I am just using the looping concept here. Move a comma has 0. 0 value I am just copying to the accumulator. Move r2 comma has 10. Just I am copying this 10 value to the r2. Next, add a comma 03. Initially, my accumulator contains 0 plus 03. Finally, my accumulator value is 03 after this instruction. Next, djnz decrement jump if not 0. The R2 value is 10 initially. Just I am decrementing by 1 to 9. Okay, 9 is not 0. I am just moving to this label to this target address. Okay, I am executing add a comma 03. What is the content of a accumulator is 03. Just adding again 03. Now I will get the result is 03. Again I am just executing this command decrement jump if not 0. Now the content is 9. I am decrementing to 8. 8 is not a 0. Again I'm just moving to this location. Okay, this loop will continue until 10 times. After the 10 times I am just checking decrement jump if not 0. This register value is 0. Then I will go to the next instruction, move a r5 comma a. Okay, a contains complete result 30 value. That 30 value I'm just moving to the r5. This is the mainly use of this looping concept. Okay, if the looping concept is not available, we need to write the very much 10 times these instructions for 10 times. Okay, here mainly here I'm using the counter with 10. Okay, here this is a r2 raised is a 8-bit register. We can repeat the loop until 255 times. If I want to repeat more than 256 times, we can write the nested loops. Okay, here if I want to repeat the actions more than 256 times, then I can use this nested loop. Okay, we will write a one program and we will use the nested loop. How we will write the nested loop? Write a program to load accumulator with 55 and complement the accumulator 700 times. See here the it is telling about this statement more than 256 times. That's why we need to write the nested loop. Move a comma has 55h. This is the first statement. It should load with accumulator with 55. Move r3 comma has 10. Okay, just I am moving the r3 with 10. This is my outer loop. My inner loop move r2 comma 70. Okay, this is my 70. I am just loading with the inner loop. Okay, next complement of A. Just I am complementing what is the content of A with accumulator. Okay, just 55 I am just complementing. Just I will get AA. Okay, zeros will be 1 and ones will be zeros. Okay, decrement jump if not 0. This R2 content I am decrementing by 1. See, 70 decrementing by 1, 69. 69 is not 0. I am jumping to here. Okay, this loop will be continued 70 times. After the 70 times I am going to here decrement jump if not 0 or 3. Okay, this 10 value I am decrementing by 1, 9. 9 is not 0. I am just moving to here. Again I am loading with R2 with 70. Okay, again this loop will continue 70 times. Okay, 70 times multiple 70 times, this R3 is 70 times, that finally 700 times we are repeating with a complement. Okay, these are mainly nested loop. Okay, next we'll discuss about the conditional gems. Okay, jump if a certain condition is met. Okay, mainly conditional gems are all are the same way. Okay, if the particular condition is met, then we are going to the that respective label. Otherwise, next instruction. Move a comma r0. Here the gem if zero label. Here we need to mention the label. Okay, move a comma r0. Okay, I don't know about the initial r0 content, just I am copying to the accumulator. Just here I am checking jump if 0. Okay, if the accumulator is 0 or not, I am just checking. If it is 0, I will just move to this label. If not, I will go to the next locations. Okay, next move a comma r1. I don't know about the initial content of r1, just I am moving to the accumulator. Here just I am checking whether my accumulator content is 0 or not. Jump if 0. If my accumulator content is 0, nothing but R1 also 0. Okay, if the R1 is 0, just I am moving to this location. If not, next locations. These are mainly use of this jump if 0. Next, we'll write one program with jump if not 0. Okay, determine if R5 contains the value 0. If so, put the 55. Okay, here first we need to check if the R5 content is 0. If it is 0, just we need to put the 55 to this R5. Okay, this is the mainly statement. Move a comma R5. I don't know about the content of R5, just I'm moving to the accumulator. Okay, here jump if not 0. Okay, not 0, I'm moving to here. If it is 0, next instruction. Okay, move. Okay, here if it is next, if accumulator content is 0, nothing but if R5 is 0, okay, just I'm moving to here, I'm just loading with 55. Okay, this is the mainly use of jump if no 0. Okay, these are the conditional statements. Okay, next we'll discuss another conditional statement, jump if no carry. Okay, here the carry carry is not 0, we need to jump to the respective label. If the carry is 1, then to the next instruction. Okay, if the carry is 0, if no carry means if the carry is 0, we need to move to the that respective label. If not, next instruction. Okay, we will write one program using this jnc. Okay, find sum of the values 79h, f5h and e2h. Put the sum in register or not, and carry will put into the r5. Okay, move a comma has 0, just 0 value. I am just clearing the accumulator. Move r5 comma a, and r5 also I am just copying the same content with 0, and add a comma 79. This is the first byte I am adding to the accumulator. Then initially my carry is 0, that's why I am directly jumping to this label. Okay, jnc jump if no carry. Okay, my carry is 0, right? I will directly jump to here. Next, add a comma f5. Okay, here already a contains 79 plus f5. Now here I got the carry is 1 and result is 6e. This 6e I am storing to the accumulator. Then carry, I got the carry, right? Jump if no carry. No, I got the carry. I will go to the next instruction. I won't jump to this location. Now I got the carry. I am going to the next instruction. I am incrementing the R5 content. Now the R5 value is 1 now. Okay, now here my R5 value is 1. Yes. Okay, next add a comma e0. Okay, now I got the 6e here. After finally I am adding this final byte to the e2. Okay, finally I got the result is 50, carry is 1. Okay, here is jump if no carry. Okay, I got the carry here also. That's why I'm going to the next instruction. I'm incrementing by 1. Okay, R2 again I'm incrementing by 1. Finally my result is R2 R5 is 02. Next move R0 comma A. Okay, here the A result it contains 50. 50 is my just I am moving to the R0. Okay, finally my R0 contains 50 and two carries. R5 is 0 2. Okay, here I got the one carry and here I got the another carry. Finally R5 is two ones, and here the R0 it contains the final result 50. Okay, this is the mainly use of the conditional statements, and we'll discuss all the condition statement here. Jump if 0. For example, if the accumulator content is 0, just we are moving to the that respective label. If not, next location. Jump if no 0. If the accumulator is not 0, we are moving to the respective location. Otherwise, next instruction. Decrement jump if not 0. Okay, here I am just decrementing the content of register. If not 0, moving to the another location. Otherwise, next location. Okay, compare jump if not equal. Here I am just comparing these two byte and accumulator. If not equal, just I am moving to the that respective label. If not, next instruction. Compare jump if not equal register with immediate data. Just I am comparing with the register with immediate data. If both are not equal, just I am moving to the respective location. If not, next location. Jump if carry. If I got the carry, then I am moving to the that respective label. If not, next instruction. Jump if no carry. If the carry is 0, I'm just moving to the that respective label. If not, next instruction. Jump if bit. If the bit is 1, then we are moving to the respective label. If not, next instruction. Jump if no bit. If the bit is not set, then we are going to the that respective location. Otherwise, next instruction. Okay, mainly all the condition state jumps are short jumps. Okay, the address of the target must be within this minus 128 to plus 127 bytes of the content of program counter. Okay, the program counter may shift within this 128 bytes of plus or minus to the program counter. For example, my location is at 10th location. Okay, I can maybe shift to the previous to the 0 or plus to 127. Okay, within this 256 bytes only we can able to shift our program counter. Maybe plus 127 or minus 128 bytes only we can shift our program counter using this short jumps. Okay, all are short jumps. Okay, we can discuss about short jumps and long jumps here. Okay, here the long jump is the these two are unconditional. Okay, here these are the conditional gems. Whenever this condition is met, we are going to move to that respective location. But here without any condition, just we are just moving to that particular label. Okay, L jump means just will jump without any conditional, and the short jump also unconditional statement. Okay, these two are unconditional statement. Okay, this is a 3 byte instruction. First byte I am storing the opcode, and the second 2 bytes, 2 byte and third byte, and the second byte and third byte I'm storing 16-bit address. Okay, we can using this long jump, I can move our microcontroller from complete program memory within 64 kilobytes of memory. We can move by using this long jump. Okay, short jump means we can move up to, okay, here all conditional jumps are also short jump, and the s jump also short jump. Okay, s jump also within the short jump we can, this is also 2 bytes. First byte we are storing the opcode, and second byte we are storing the relative target address where we want to move. Just we are storing the second byte. Here for the long jump, second and third byte we are storing the address is a 16-bit. We can move wherever we want using this long jump. Short jump we can move within this 128 bytes of plus or minus. Okay, next one we'll discuss to calculate the target address of the short jumps. sjump, jnc, jz, these are the conditional statements, and also unconditional sjump also comes to these short jumps. Okay, all are short jumps only. Next, the second byte added to the program counter, the instruction immediately below the jump. Okay, for example, wherever we want to move our program counter, whenever the condition met or the short jump, then finally we are storing the second byte to the address. Okay, if the target address is more than minus 128 to plus 127 bytes from the address, the below short jump instruction. Okay, mainly for example, if the address target address is more than minus 128 to plus 128 bytes of program counter, may assembler may give the error. Why? Because these instructions should use within this minus 128 to plus 127 bytes of memory. Okay, for example, if it is exceeding that, we should not use these short jumps. We need to use this long jump. Okay, mainly. Okay, this is the mainly use of this long jumps and short jumps. Okay, then we'll take one example how we'll calculate the address and how we are putting into the opcode. Okay, this is my code. Jump if 0. Okay, if my accumulator content is 0, I'm just moving to this location. Okay, here assembler it will calculate the relative address and it will put to the second byte of opcode. Okay, as we discussed here. Okay, short jump is the 2 byte. First byte is the we are storing the opcode, second byte is the relative address. Long jump also, first byte we are storing the opcode, second and third byte we are storing the relative address. This is the 16-bit address, this is the 8-bit address only. We can jump up to within this 128 bytes of memory. Okay, here all the sjumps and all the conditional statements are short gems only. We can just move up to within this 128 bytes of memory. For example, here jz, I'm just moving to this relative location whenever this condition is met. For example, jz is my opcode is 60, and 03 is my relative location wherever I want to shift. Okay, here assembler it will calculate 1 2 3. Okay, 3 times it will add to the accumulate program counter. Whenever this condition is met, then I need to move our microcontroller control to here, 3 bytes front. Okay, here whenever I am executing this instruction, my program counter will be located here. I am just incrementing with 3, 1 2 3. Okay, whenever this condition is met, okay, my program counter is here, I am just moving to here. Okay, similar way we'll discuss about the another instruction also. Jump if no carry to the over. Okay, to here I need to move. Okay, similar way it will calculate how many bytes, and it will just add to the second byte. Okay, 5. Okay, currently my program counter is here. Currently I am executing this instruction. My program counter is here. I just want to move the 5 locations. Okay, whenever this condition is met, I want to move to the 5 location. 1, 2, 3, 4, 5. Okay, whenever this condition is met, our controller directly here, it will assembler, it will store the address here. Whenever this condition is met, it will go to this relative address. Okay, by using these short gems within this 128 bytes only, we can shift either positive or negative. Okay, we'll see about the negative addressing. Jump if no carry again. Okay, here I am just moving to here to here to the negative addressing. Okay, negative addressing will start from the ff fe fd. Okay, I need to just minus with 13 locations, then finally I will get the f2. Okay, these are mainly negative addressing and positive addressing. Okay, here as we mentioned here, right, minus plus 127 to minus 128. Okay, here minus 128 to plus 127 bytes only we are able to shift. Okay, this is a negative addressing. From ff2 we need to come back. This it will treat as a negative addressing. If it is positive, then the msb bit won't set to 1. Okay, this is the mainly difference of the positive and negative addressing for the short gems. Okay, these are all are the short gems. S jump, all the conditional gems are short gems. Okay, for the long jump, we can jump to any relative location by using this 16-bit address. First byte is opcode. Okay, next we'll discuss about the L call and A call. Okay, mainly for the subroutines we can use this one. Subroutine means subprogram. Whenever we want to call from the main program to subprogram, mainly this long call and A call can be used. Call instruction is used to call the subroutines. Subroutines are often used to perform a task that need to perform frequently. Okay, for example, I want to write any delay function. Okay, I want to call whenever I need to I need require any delay, I can call to that program. Okay, this makes a program more structured in addition to save memory space. Okay, mainly we can use this L call and A call whenever we want to call this subroutine. Okay, 3 bytes instruction. Okay, 3 bytes means first byte I am storing the opcode, and second byte and third byte is a 16-bit address. Okay, we can jump to any location in our complete 64 kilobytes of memory. For example, a call can be used within this 2 kilobytes range only. We can use this absolute call. Okay, for example, within 2 kb my subprogram is available, I can use this a call. For example, more than 2 kb my subprogram is allocated more than the 2 kb, I can use long call. Okay, next we'll discuss in the next slide how the operations. For example, this long call or a call. For example, long call we can use whenever my subprogram is located more than 2 kb, I can use long call. Let us assume this is the long call, whatever we are discussing about. Okay, long call delay. Okay, delay is my subprogram, I am just calling to here with long call. This is my function subprogram. Delay is my subprogram. Okay, here it is located with 300h. Right now, my execution at the, let us assume 0, 1, 2, 3. Let us assume location 3. Okay, just I want to move to the 300h so that I can use the long call. If it is more than 2 kb, I can use the long call. Okay, just I am moving to here. Whenever I am moving to the subprogram, I have to store my the next instruction address to the stack memory. Okay, mainly use of the stack. We have the stack memory pointing at 07. Okay, that we will discuss in the next slide. Just mainly here we will understand whenever my microcontroller control from here to here, my program counter holding the address here. Okay, this address I will copy to the stack pointer, then I will move to our program counter to this address. I will execute this complete instructions. Then whenever this ret is called return, okay, I will retrieve the address from the stack memory to again program counter back. Again I will start executing from here. Okay, just understand how the flow is. Just whenever this lcall is called, whatever the program counter address we are storing to the stack pointer. Okay, and I will go to the new address with the program counter. I will execute this complete instruction. Whenever the ret is called, we need to retry from the stack memory, whatever the address we saved, right? Again, I will retry from the stack pointer. Again, I will execute from here. These are mainly if you want to execute any subprogram. Okay, we'll understand how we were generating delay here. Okay, here delay, whenever I'll call delay, I have called here, my PC counter will come to here directly. Move r5 comma has 55h. Okay, this I'm just treating it as counter with, I'm just loading the max value of 255. Okay, djnz I'm decrementing with 1, 255 I'm decrementing by 1, 254. And if it is not 0, I'm just going to this again here. Okay, this loop will be continued 255 times. Okay, here again I will decrement. If not 0, I will go to here, decrement. Again not 0, I will go to here. Okay, this statement will execute until 255 times. After that, I will go to the return. Return means I will retry the address from the stack pointer to program counter back. Again program counter start executing from here. Okay, this is the mainly sequence of the subroutines. Okay, here we'll see how we are storing the, whenever the alcohol is called, alcohol delay. Okay, the next instruction address we need to save to the stack pointer. Okay, this is my next instruction address, this is my subprogram I need to move. Whatever the next instruction always pointing my program counter. Okay, this address I am just copying to the stack pointer. Okay, always stack pointer will starting with 07. Whenever the first byte is pushed, then it will be targeted to 08 address. Okay, here 0007, just 07 I am moving to the first byte, and 00 next byte. Okay, whenever this ret is called, again we will retry from this program counter, from the stack pointer to again program counter back. Again we'll start executing from here. Okay, this is the mainly use of the stack pointer. Okay, next, if we have so many subroutines also, we are going to store to the stack pointer. Again, we are retrying from that. We can execute many subroutines as usually. Okay, here a call, absolute call. Only the difference, whenever this long call can be used within this 64 kilobytes of memory. If you want to move our microcontroller, we can use this long call. A call within this 2 KB of memory. Okay, next, here a call, I'm just using absolute call. Instead of that, yeah, anyone we can use. Here just move. Here I'm just writing one of the program. Here move a comma 55. Move port 1 comma a. Whatever the content of a, I'm moving to the port 1. A call delay. Okay, just I'm calling to the same delay function as we discussed previous. And I'm just complementing a 55. I'm just complementing with a. And short jump, here I'm just using the short jumps is the, just it is a unconditional jump within 128 bytes of memory we can shift. Okay, this program, this complement, this sjump, always this is infinity program we are executing. Sjump here means infinity times we are executing this statements in infinity times. Mainly this is the mainly use of this one. For example, if we want to execute our program infinity times, see here indefinitely. Keeping this loop in indefinitely means infinity loops, I'm executing this back to back. Whenever my execution here, again I'm going back to here, again here. This is a continuation. If you want to execute, I can use this short gems mainly. Okay, here how to calculate the delays in our 8051 we'll discuss from here. Okay, for example, CPU executing an instruction takes certain number of clock cycles. Yes, it's correct. For example, each instructions it will take one machine cycle. One machine cycles contain 12 clock cycles. The length of machine cycle depends on the frequency of the crystal oscillator connected to the 8051. Okay, here mainly this machine cycle period mainly depends on the 8051 external microcontroller frequency. In original 8051, one machine cycle lasts 12 oscillations periods. Okay, that's why here we'll calculate period. Okay, find the period of the machine cycle. For example, I am giving the 11.0592 megahertz to the our 8051 microcontroller. Then we'll calculate the machine cycle period. 11.0592 megahertz divided by 12. I will get the 921.6 kilohertz. Okay, machine cycle period is 1 divided by frequency. This is my machine cycle period, 1.085 microseconds. Okay, if I want to execute any instructions, it will take one machine cycle, nothing but 1.085 microseconds. Okay, this is every instruction it is taking this much time whenever my frequency is 11.0592. Okay, basically in our 8051 microcontroller, always we are connecting this frequency. We should remember this timing for each and every instruction execution. It will take 1.085 microseconds. Okay, similarly we'll calculate the time period. For example, well, for the first instruction move r3 comma 55, okay, it is taking one machine cycle. That's why 1 multiply 1.085 microseconds. Finally it will take this much time to execute this instruction. Similar way for the second instruction also it is taking the same timing, and the third, fourth, fifth also it is taking the two machine cycles, 2.17 microseconds. 2 multiply 1.085 microsecond, then 2.17 finally. Okay, similarly for the last instruction mul AB, it is taking 4 machine cycles. 4 multiply 1.085 microsecond, 4.34 microseconds. If I want to execute this multiplication operation, it will take 4.34 microseconds. These are mainly how to calculate the mainly timing of the each and every instruction. Okay, here find the size of the delay in following program if the crystal frequency is 11.0 finite. Okay, for example I am just giving this external frequency, then we need to calculate how much delay is taken to execute this delay function. Here see, whenever move a comma has 55 55, I'm just moving to the accumulator. Move port 1 comma a, just I'm content of a, I'm just moving to the port 1. A called delay. Okay, just I am moving to this sub function move r3 comma 200. Let us take, it is taking one machine cycle, and decrement jump if not 0 r3. Okay, this is 200, I am just decrementing by 1, 199, and if it is not 0 I'm just moving to here. Okay, this loop will continue until 200 times, and every machine cycle is 2. Okay, every instruction time is 2. 2 into 200 totally, this is a second instruction. For the first instruction is the 1, okay, plus 1, and the last instruction is 2 machine cycle it is taking plus 1. Okay, finally these many instructions we have multiply 1.085 microseconds. Okay, finally 436.255 microseconds it is taking if I want to execute this delay function. Okay, these are mainly, if I want to increase further I can use the nested loops or some other loops. So, okay, we'll discuss in the next slide. Okay, this is the for the normal loop we can execute up to we can just repeat our execution up to 436.255 megahertz. Okay, here microseconds. Okay, next here by using no operations also we can increase the our microcontroller delay. Here I am just writing my delay program using the no operation. Delay, this is my sub function subroutine move r3 comma 250. Here no operation, no operation, no operation, it is taking one machine cycle. For the four no operations it will take four machine cycles. And dj and z I'm just decrementing by 1, 250, 249, and if it is not 0 I'm jumping to here. Okay, this instruction will execute until 250 times. Okay, 250, here 1 1 1 1 4 ones plus 2. Okay, this is the plus 2. Okay, this it will execute 250 time 250 times. That's why I'm just multiplying with 250 times, and I got the 1627 microseconds, and adding two instructions outside loop we have. Okay, here I'm just adding this one and this one. Finally for the delay, the first instruction it is taking one machine cycle, and last one two. Finally I am adding this result to with the three machine cycle. 3 multiply 1.085, finally 16,30755 microseconds. Okay, similarly we can calculate the delays when we have the these many instructions. We can calculate the exact delay by using these calculations. Okay, next is a large delay using a nested loop. For example, if I want to increase further delay more than this, let us take more than 1630 microseconds. If I want more than this, so that I can use this nested loops. Okay, as we discussed in the initial case, nested loop and normal loop. In case of nested loop we can repeat our loop in the outer loop and inner loop way. Okay, delay move r2 comma has 200, I'm just moving to here. Move r3 comma 250. Okay, here for the first, this is the outer loop, this is the inner loop. Okay, here no operation, no operation, it will take one machine cycle. This also one. And dj and z, just I am decrementing 250 with 249, and it is not 0, I'm jumping to here. Okay, this loop will continue 250 times, and after that decrement jump if not 0 r3. Okay, here r2, here 200 will be reduced by 1, and here the finally reduced to 200 reduced to 199, and again I am shifting to here, And just repeating, I'm just reinitializing R3 with 250 times. Here 250 multiply into 200 finally. Okay, this much delay we can reproduce. Okay, here the loop we are calculating. We have the 4 into 250 times. Okay, here 1, 2, 3, 4. Okay, inner loop. Just I'm calculating here to here. 4 multiplied 250 times I am repeating. I got this 1085 microseconds. Okay, here 1085 microseconds. I am just repeating how many times? 200 times. Okay, 200 into 1085 microseconds. And finally, I will get 217000 microseconds. Okay, then first instruction and last instruction also we need to add. Move R3 comma 250. Okay, here the 250 and DJ R2 comma again at the start and end of the again loop. Okay, here three machine cycle. Okay, 1 plus 1 3, 1 plus 3 machine cycle into 200 times. Okay, this is the last cycle return, right? Okay, this is the 200 times. Finally 651 we need to add to the previous one. 217000 plus 651 equal to 217651 microseconds. Okay, finally if you use this nested loop, we can increase our delay as much as possible. Okay, by using two counters we can increase, by using a nested loop we can increase as much as possible. We can create the delay by using these instructions in our 8051 microcontroller. Thank you friends, thank you for watching.